So the next cool thing that I'm going to show you is something called the crossed Aldol reaction. So far, every single Aldol reaction that I've shown you, the addition reactions as well as the condensation reactions, every one of them has been with two identical aldehydes reacting together, but that is not a requirement. You can have an aldol reactions between two different aldehydes or ketones, and when we do that, we call it a crossed aldol reaction. And the crossed reaction produces up to 4 different products, not counting stereoisomers, not counting cis strands, produces up to 4 products, excluding the stereoisomers. So this is how we can get up to 4 different products. So let's say that we're going to call our aldehydes A and B. So let's say that we have A reacting with B. Well, when A and B react together, there's 2 different ways that they can react. Either A can become the enolate and attack B, and that would give you 1 product, or B could become the enolate and attack A, and that would actually give you a different product, even though it seems like maybe they should be the same. And then even though we have 2 different aldehydes in there, there's nothing that's going to stop an A from reacting with an A and a B from reacting with a B. So that gives us a possibility of 4 different constitutional isomers, and then even more if we're counting cis and trans. So let's take a look at how we can get that many products from a crossed reaction. And let's go back to this worksheet that we're working on. The same one we're working on. Here is a crossed reaction, and we're being asked to draw all the possible products, and whenever possible we should make the reaction go all the way to condensation. So it's kind of tedious when you're being asked to draw all the possible products, and this is not including stereoisomers. We're just looking at the structural isomers. It's a little bit tedious, but we're going to go through it. And we're going to work on finding some shortcuts instead of drawing the mechanism every single time to make it less tedious. So we are going to start with, let's say I'm going to draw alpha hydrogens onto this first molecule. So let's say that the molecule on the left, let's call this guy molecule A, and our other one, let's call him molecule B. Let's say that molecule A is the one that becomes the enolate. So it's got a negative charge right there, and it is going to attack molecule B. And like I said, I'm not going to do the whole entire mechanism here. We're just kind of do half of a mechanism. So here is molecule B after it was attacked. It's got the negative charge on its oxygen, and we have connected it to molecule A, and I am counting my carbons, 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, 1, 2, 3, 4. I connected 5 to 2. Yes, that looks good. So there that product is, and then remember in the next step in the reaction, we're going to protonate. This is so easy with an eraser. So we get this guy. And then we would, I'm gonna redraw this looking nice and clean. I'm gonna clean it up. Carbon 1, 2, 5 has the OH, 6, 7, 6, 3, 4. 1, 2, 3, 4, 5, 6, 7. So there it is, nice and pretty. And can we do a condensation on this guy? Well, in order to do a condensation, we need to focus on the OH carbon as well as the alpha carbon. Is there a hydrogen on that alpha carbon? Yes, there is. And so we can remove it. We can remove the OH. And we're going to make this a reaction, and we're going to stick a double bond right there. And yeah, we're going to have cis and trans, or E and Z, however you want to think about it, but that's not really what we're focusing on right now. So there's one possible product that we can make. So let's consider option number 2. Let's have same A, and let's draw his alpha hydrogens in, and we're reacting with B. And we'll draw those alpha hydrogens in, And this time, let's have B become the enolate. So we want to put a negative charge on the alpha carbon of aldehyde B. Then go ahead and have that guy attack aldehyde A, open up that carbon-oxygen double bond, and let's draw what we get. We've got aldehyde A with its double bond opened up, like that, and we are making a connection to aldehyde B. I think that this is what it looks like, but I need to number my carbons. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 5. Yes, no, that's not carbon number 5. 5, 6. No, that's still not carbon number 5. I have made a numbering error. 5, third time is a charm. 6, 7, there we go. And that O negative is going to get protonated. So we have that guy right there. Let's draw it nice and cleaned up. Maybe it's just going to be an identical molecule. I'll make an equals sign. There's carbon number 5. There's 5. Connect to carbon number 6 and connect to carbon number 1, which is our OH carbon. Then connect to 2, 3, 4, 2, 3, 4. And don't forget that 6 has a random methyl as well as carbon number 7. So there it is. And can we do condensation on this guy? Let's see if we can do condensation. So first we have to find our OH carbon as well as our alpha carbon. In order to do condensation, we need to have an alpha hydrogen on carbon number 6, and there is not one there. We cannot do any further reaction on this guy, so that's our product number 2. And so let's continue on. The next thing that we could have happening is a molecule A reacting with another molecule A, 2 identical molecules. So for this, let's make the left-hand molecule A the enolate, and it is going to attack the carbonyl carbon of the right-hand molecule. Let's draw the right-hand molecule with its bond opened up and its carbon chain, and we're making a connection to the other molecule. I think that I'm doing this correctly, but I'm going to number my carbons to be safe. 1, 2, 3, 4. 1, 2, 3, 4. 5, 6, 7, 8. 5, 6, 7, 8. Looks good. Protonate your oxygen. And let's redraw and see what we have. Carbon number 1 to 2 to 5, which has the OH, to 6, 7, 8. 1, 2, 5, 6, 7, 8, and carbon number 2 has 3 and 4 attached. Now, can we do a condensation? We're going to look at the OH carbon. We're going to look at the alpha carbon. Does the alpha carbon have a hydrogen on it? It does. If it has a hydrogen on it, we will dehydrate, put a double bond in between those 2 carbons. There will be cis and trans. This is molecule number 3. And then for our last molecule, we are going to have molecule B reacting with molecule B. So I'm going to draw 2 molecule Bs. Let's make the one on the right hand, we'll make that be the enolate, and we'll have it attack. I said right, I meant left. The one on the left is the enolate, and it will attack the molecule on the right. Let's draw the molecule on the right with its bond opened up. That's what it looks like. Let's number its carbons. 1, 2, 3, 1, 2, 3. We are attacking with carbon number 5. 5 is going to 1, so there's carbon number 5. It attacked 1. 5 is connected to carbon number 4, which is a carbonyl carbon. 5 is also connected to carbon 6. And a methyl that doesn't have a number. So there we go. And then we're going to magically protonate that O-. Let's draw that a little bit straighter and a little bit nicer. There's carbon number 4. There's 5. 5 has 2 methyls on it. There's carbon number 1 with its OH, 2, 3, and a random methyl. 4, 5, 6, 1, 2, 3. Can we do condensation? We look at the OH carbon, we look at the alpha carbon. The alpha carbon does not have any hydrogens on it, which means it cannot react further. And there's all 4 of our beautiful products.